Let's thank Eanna Flanagan, who is going to tell us something, but I don't have his title in front of me, so he'll tell us.
Okay. So my title is gravitational.
Is the microphone on? No. Maybe is there a switch or something?
Can you hear me now?
Okay, great. So I'm going to be talking about gravitational phase spaces and horizons. And it's going to be based on a recent paper with Len Chandrasekaran. And here's the archive number. And also, I'll be touching on a slightly older paper with Ben and my other collaborators, Anthony Speranza, and my graduate student, Ibrahim Shahzad. Okay, and then I should also mention that this paper that I'll be talking about has some overlap with two papers that came out almost simultaneously. One was by Gloria Odak, Antoine Rignon-Brett, and Simone Spatial, 2309038854, and one by Luca Chiambelli. This is a different paper, Laurent Friedel, and Robert Lay. 23090932. So these papers overlap a fair amount, but they're quite different in sort of their interpretation and their focus and motivation. And actually, Luca is here, and he's going to be giving a talk later on today on the results of this paper. So I'm going to try and focus on the things that are different between the two papers, so as not to have too much overlap between the two talks. Okay. So to start off, I'm going to be talking about gravitational phase spaces. So for concreteness, let me start off with the Schwarzschild, maximally extended Schwarzschild metric, which has this conformal diagram. And now I want to consider vacuum metrics that are nonlinear perturbations of this, but still have the same basic structure. And in that case, we can, in any perturbed spacetime that still has this conformal diagram, we can look at the initial data on the future horizon here and the future horizon here. And that initial data, say for vacuum general relativity, will determine the metric in here. And then we consider the set of all such possible constructions, and that's going to be the gravitational phase space, at least one example of the type of gravitational phase space I'll be talking about, the set of all metrics associated with these surfaces, the future horizons. One important point here is that these horizons are uniquely determined functionals of the metric of the your point in phase space, which will be an important point later. So we can always gauge fix to, in all the different solutions, make the horizons be at the same location on the manifold, which we will do. So I'm going to be focusing on this type of phase space, basically inside the black hole. But of course, you can also consider a similar phase space out here, parameterized, say, by initial data on the past horizon past till infinity. And the other type of phase space, of course, is a gravitational scattering, where we consider initial data on past null infinity and final data on future null infinity, and consider the set of all metrics in the interior like this. So that's one type of gravitational phase space that I'll be talking a lot about. But then the second type of gravitational phase space is basically a nested sequence of subphase spaces. So the idea is, coming back to this diagram, I fix a surface or a cut of, say, the future event horizon. And instead of considering, say, all the data on these two surfaces, I just consider the data to the future of this cut. And I consider the corresponding media of the metric that's determined by that. So that's a subspace. And again, I consider all possible initial data associated with that. But now I have a subspace associated with a cut of the horizon. And a similar construction at future null infinity gives me a subspace up here. And this subspace of future null infinity is associated with charges like the Bondi mass and other BMS charges. And so what I'll be talking about in this talk is things that are analogous to the Bondi mass that basically tell me the amount of radiation that passes the future null infinity to the future of some cut, but analogous constructions for black hole horizons. How do we define such objects and so on. So I'm interested in sort of how do I construct the phase space? What's the symplectic structure? Are there any ambiguities in the symplectic structure and so on? And what is the boundary symmetry group in all of these different cases? So here I just mean the set of diffeomorphisms that act on the space-time, that preserve all the boundary conditions that I impose, and then mod out by the trivial diffeomorphisms that are not degeneracy directions of the symplectic form. So that's what I'm going to be talking about for symmetry groups. And then what are the associated generators? Things like the Bondi mass. Okay, so that's basically where I'm going. What are the motivations for studying these questions and for these specific spaces? There's some connection, of course, to observations. So as you know, studying the various symmetry groups at future null infinity is closely related to gravitational wave memory, which people hope to measure. And new types of gravitational wave memory have been discovered associated with enlargements of the usual symmetry group. And then there are analysis things that happen at black hole horizons. There are quantities like memory. There, of course, we won't be able to measure them in practice, but in principle, you can imagine similar observations near black hole horizons associated with things that are like memory. And the other main motivation, of course, is that understanding just in the classical theory what the symmetry algebra is can help you in trying to find the quantum theory, like in the celestial holography program. And lastly, the algebra of symmetries has been used by Strominger and others to derive the Bekenstein-Hawking entropy of black holes. So before going on, let me just talk about some of the restrictions or limitations of what I'm going to be talking about. So I'm going to be focusing on vacuum GR in 3+1 dimensions, just specific, to keep things specific. I'm talking about symmetries, but I'm restricting to diffeomorphism symmetries only, space-time. Symmetries only, or other important symmetries that can be studied asymptotically even in vacuum GR, but I'm just for concreteness going to restrict to this case. I'm mostly going to restrict attention to this case of this phase space inside the horizon. And that's just because studying things on a null surface at a finite location is technically easier than going to null infinity, because here things are divergent. One has to worry about various schemes for renormalization and so on, which make things more complicated. But ultimately, you would like to unify those two things together. Okay. All right. So so my goal is basically to talk about different possible definitions of gravitational phase space and to talk about the derivation of the corresponding symmetry groups. So I'm going to start by reviewing sort of the story at future null infinity, and then talk about the analogous story for black hole horizons. So Let's draw this diagram again. Say a piece of maximally extended Schwarzschild. And I'm going to talk a little bit about future non-infinity. I'm going to use boundary coordinates. U, theta 1, theta 2, theta A. And then, so we're interested in what are the symmetries, which mean what are the diffeomorphisms that preserve all the boundary conditions I impose that are not trivial, they're not degeneracy directions. And so all of the different, symmetry groups that people have derived in the last few years can all be written in the following way. It looks like this. So this summarizes all of the different possible symmetry groups. So the angles get mapped into themselves. So just a diffeomorphism of the two-sphere. And then U, which is a parameter along the null generators, has this transformation that consists of a translation part and a rescaling part. So the different symmetry groups are the Bondi-Metzner-Sachs group from the 1960s, which we can summarize as the Lorentz group, semi-direct product of supertranslations. And in this case, this mapping is basically a Lorentz transformation. This rescaling is determined as a function of the Lorentz transformation, and this is a free function which is parameterized as supertranslations. And then that has been extended in two different ways. So there's the generalized BMS group, which you can write as diff S2 semi-direct product supertranslations by Campiglia and Nada from 2015. So this is a generalization of the group where the Lorentz transformations are replaced by arbitrary diffeomorphisms of the two-sphere. That's the only change to the group. And the other transformation is the extended BMS group, which I'm going to write as WIT supertranslations, which instead changes these transformations to be local conforming or local conformal isometries instead of global conformal isometries of the two-sphere. And this is due to Barnich. 2010. And then more recently, there's been another extension of this group here. Which is called the Weil BMS group, which is the diff S2 semi-direct product with supertranslations. And that's basically given by exactly the same formula. This is now allowed to be an arbitrary diffeomorphism. We still have these supertranslations. And this factor in front is no longer constrained to be determined by the diffeomorphisms allowed to vary freely. So it makes it a larger group. And this was Friedel et al. In 2021. And there's also an extension of this algebra more recently to this wedge algebra by Andy Strominger, which is an even larger group, but that is no longer just based on diffeomorphisms, it goes beyond those. Okay, so that's the background for the different various symmetry groups at future null infinity. And so natural question is, sort of what's the analogous story at black hole horizons? What are the various symmetry groups and so on? So, so this subject of studying symmetry groups at horizons started back in 2016 with a paper by Andy Strominger and Stephen Hawking and Malcolm Perry, arguing that there should be analogs of BMS supertranslations on horizons and that they should have important consequences. So I'm just going to summarize 4 different choices of phase space that you can make on a horizon and what the 4 different symmetry groups are. So I'm going to start with the smallest group. So there are 4 groups. So the smallest group I'm going to write it as diff S2 semi-direct product while super translations. So this group is a group that my collaborators and I derived a few years ago. So I'm going to go through in a little more detail where this comes from, what do you have to assume to get this group. Its group structure is actually identical to the while BMS group that was uncovered later at Future Null Infinity by Laurent Fidel and his collaborators. So it has the same group structure. It's derived in a different way because the way things work at Future Null Infinity when various things have diverged is very different from what happens at a finite location on a horizon. Okay, so that's the smallest group. There's a slightly larger group. So a difficulty with this group is it's based on a certain gauge fixing. And just like the original analysis of the bonding metrostatic group at Future Null Infinity, which was based on a gauge fixing that people later realized was unphysical. You were fixing a degree of freedom that was not gauge. It was actually a physical degree of freedom because it did not correspond to the degeneracy direction of the symplectic form. This analysis of a symmetry group and so on had the same problem, that it was based on a particular gauge fixing that I will explain during the talk. But again, you could show that it wasn't, it was too much gauge fixing. Certain degrees of freedom were fixed, which even though they are diffeomorphisms, they were not gauge, they were physical. And so we need larger symmetry groups. So there's a slightly larger group, which I'm going to call diff S2 so arbitrary reparameterizations. So this group is basically arbitrary diffeomorphisms of the two-sphere, and then along the null generators, there are arbitrary reparameterizations allowed, which is different from what goes on over here. The reparameterization has to be this affine transformation. These transformations are sometimes called Carolian diffeomorphisms because they preserve something called a Carroll structure. Then there's a slightly larger group that one can define, which is the same thing. Semi-direct product, these arbitrary reparameterizations. And then I'm going to, there's a new degree of freedom that comes in that I'm going to call a while transformation, kind of a rescaling. It's a piece of the four-dimensional diffeomorphism that's no longer characterized just by the three-dimensional diffeomorphism in the boundary, just an extra piece. And then the largest symmetry group that one gets is basically what I call a diff of the horizon semi-direct product while. This symmetry algebra was actually derived a few years ago by Adami et al. It's now arbitrary diffeomorphisms, three-dimensional diffeomorphisms on your boundary surface, your horizon, and then there's an extra piece of the four-dimensional diffeomorphism that also comes in. Okay, so those are all the different symmetry groups. One of the reasons that it's sort of interesting to study these symmetry groups is because there's going to be an interplay between these groups and the various groups of Future Null Infinity, and particularly when we want to understand global conservation laws associated with these groups. So several years ago, Andy Strominger argued that even in the original BMS context, that there's a global conservation law for scattering in this type of space-time up here that basically says something like Q scry minus is equal to Q scry plus. In other words, it's a quantity you can compute from data on past null infinity, and it has to match a corresponding quantity from data on future null infinity. And there's such a conservation law for every generator of the group. And the appropriate group that Andy argued was relevant was the cross product of the BMS group on scry minus with the BMS group on scry plus. That gives you a large group, and then you take the diagonal subgroup. The requirement for taking the diagonal subgroup comes from the fact that you don't want any contribution to the conservation law that's localized near time like infinity, and that restricts you down to the diagonal subgroup and gives you the conservation law. That conservation law was proved rigorously, sort of in a mathematical sense, a few years later by Kartik-Prabhu, and based on putting in some assumptions about asymptotic flatness and so on at spatial infinity. There are corresponding laws these conservation laws have a physical interpretation of conservation of energy independently at every ingoing and outgoing angle. And there are thought to be more general conservation laws involving angular momentum and boost charge associated with these higher groups. And there are similarly thought to be conservation laws like these for those larger groups, but they've not yet been sort of proved from a mathematical point of view. But they're thought to be true. So that's the story on sort of gravitational scattering without horizons. If you now put in horizons and you ask about what's the global conservation law, what are the symmetries, then you expect a global conservation law. Let's see. Oh, yes. Okay. Okay, so yes, so when you have both horizon and future non-infinity present, you expect a conservation law that looks something like this. In other words, I compute some quantity from data on a past horizon and past non-infinity, and that should match what I get on a future horizon and future non-infinity. And that should be true for every generator of your symmetry algebra. But to actually formulate and prove something like this requires us to figure out something like an identification of symmetry generators on the horizon with symmetry generators at null infinity. And that in turn requires a sort of asymptotic analysis of what's going on at future time-like infinity or at past time-like infinity, analogous to the analysis that's already been done at space-like infinity. And one of the challenges in even attempting to do something like this is that symmetry groups on null infinity and the symmetry groups on a horizon, but not yet in concert. And so it's sort of significant that one of the groups here does actually match. The smallest group on the horizon, this group we figured out a few years ago, actually is exactly the same group structure as the largest group structure derived by Friedel at null infinity. And so one might hope to match up these groups, find a cross product group and a diagonal subgroup and formulate conservation laws. But that's sort of a speculation as to what might be provable in the future. But that's one reason for being interested in what the horizon symmetry groups are, so you can try and formulate and prove these very general conservation laws. Okay. How am I doing on time? Okay, so I want to talk now in a little bit more. So that's kind of the big picture of what I'm talking about. I want to talk now in a little bit more detail about the specific case of the phase space inside the horizon, say for a maximally extended Schwarzschild black hole. And to talk about that, I'm going to review the sort of the double null initial value formulation. Of general relativity. In other words, if I give you a space-like 2 surface and then 2 null surfaces I'm going to call S plus and S minus that intersect at that space-like 2 surface, what's the exact data that I need to specify in vacuum general relativity to determine a unique solution? So for a space-like surface, we know we need to specify the induced metric and extrinsic curvature. What do we specify here? So let me just tell you what the answer is. There are many papers that give sufficient initial data. A lot of them use specific coordinate conditions. And there's a very nice paper by Mars and Sanchez Perez that analyzes, gives sort of a very geometric and coordinate independent specification of what initial data you need. And I'm going to present sort of a slightly simplified and streamlined version of what they say. So, so basically the idea is if I give you a metric, it's going to determine some quantities on these three manifolds. And I want to figure out exactly what's the minimum number of quantities I need in order to get complete information about the metric up to diffeos. So let me just list what are the various things you need. So we pick normal one forms, L say plus A and L minus A. So I have these surfaces. I'm going to pick normal one forms to those surfaces. And then I'm going to, so these are, because they're null, they can't be normalized. So there's a rescaling freedom. I'm going to write like this. And L minus A going to sigma minus L minus A. So there's no way to resolve this ambiguity, and so it becomes a kind of a freedom, and the formula is analogous to a diffeomorphism freedom. So everything will sort of be invariant with this rescaling freedom. So that's the first thing we need to specify. Then we raise the index. To get the up index normal, and which is going to be an intrinsic vector on the two surface. And I'm going to write intrinsic vectors with indices I, J, K. So I'm going to get something like this. So I have the intrinsic normals in the two surfaces, the up index ones. I have the induced metrics. Qij on the plus surface and Qij on the minus surface, which are constrained to agree where the surfaces intersect. And then I project from these down to the conformal equivalence class. So instead of looking at the actual induced metric, I just throw away some information and just look at the equivalence class of these metrics under conformal transformations. Okay, it's 3. The 4 is then the inaffinities defined by L, say, plus A, divided L plus B, plus A. So it's this a scalar function on each surface. It's sort of like a one-dimensional connection determined by the metric. And the fifth quantity is I'm going to define a scalar quantity just on the intersection 2 surface to be minus L plus A, L plus B. Just the dot product of the two different normal vectors. Okay. I'm going to need the expansions of these two vectors. Plus and theta minus on S0. And then I need something called the H-check1 form. Which is L plus A minus L minus A. Okay. And again, these are quantities now that are just defined on the intersection 2 surface. So the claim is if I just specify all of these quantities, and then all of these quantities will transform in different ways when I make this rescaling. So what I do is I take this set of quantities and then I mod out by that rescaling, sort of take the equivalence class. And that defines then a geometric structure. And the claim is that is exactly the right structure you need to determine the unique initial data. Okay. And so then this structure. Should I go on?
Just keep going.
Okay, all right. How much time do I have left? Okay, all right, that's good. The phase space we're going to be talking about, I'm going to be basically computing a symplectic form on this phase space. And these are going to be basically the coordinates I'm using. They're going to be this equivalence class of geometric quantities is going to parameterize my phase space. And I'm going to construct a symplectic form in that phase space and also compute charges and so on. So these are basically my coordinates. I should emphasize that when we specify all these quantities, there are constraint equations on the null surfaces, basically the Ray-Chowdhury equation and the De Moivre-Navier-Stokes equation that allow you to compute, for example, the faux induced metric from the conformal equivalent class, given some of the initial data on the intersection surface. So you can show all of that. So this parameters. 5 minutes, okay. So this parameterization of the phase space needs to be extended in actually 3 different ways before I can use those good coordinates on the phase space I'm defining. So let me quickly talk about the extensions. So let's see, I'm going to go back over here and I'm now going to start erasing. Okay, so the first extension I actually can just explain in words. So this specification of data on a null surface or 2 intersections is completely general, but I'm going to apply it to two horizons, the sort of left and right future horizon in black hole spacetimes. And in that context, I can basically actually eliminate this from my definition of my phase space. And the reason is that this is really just, these expansions are really just needed as initial data to solve Ray-Chowdhury's equation. And that determines everything uniquely. But a horizon has sort of this boundary condition at late times. It tells me what the expansion is doing at late times. So I can use that boundary condition to determine the solution instead of these. So that makes the analysis simpler to have this smaller phase space where I throw it away. The second thing, which is a little unusual, is that I need to extend the set of data a little bit to include some degrees of freedom that are diffeomorphism degrees of freedom. So in space-like hypersurfaces, the geometric information is the induced metric and the extrinsic curvature, and that uniquely determines the metric in the future up to a diffeomorphism. And normally we think of all those diffeomorphisms as being gauge, and in particular, they're all degeneracies of the symplectic form. However, here things work a little differently. So once I specify this data, it does determine a metric to the future of these 2 null-lit surfaces. And that metric is unique up to diffeomorphisms, but there's one piece of that diffeomorphism that's not a degeneracy of the symplectic form, which is not gauge, which we need to include. And so let me just, I'm going to need this guy. Well, actually, I'll just erase this. And that's basically, if I have a 4-dimensional diffeomorphism on the manifold, and I act as a pullback on the normal vector, then because the 4-dimensional diffeomorphism is assumed to preserve the boundary, it has to preserve the normal up to a rescaling. So there's some function on the surface that rescales the normal associated with the 4-dimensional diffeomorphism. So it's analogous to the lapse function for space-like hypersurfaces, but this quantity is not a degeneracy direction of the symplectic form. So I can incorporate that basically by adding one additional item to this set of initial data, the down index normal, and again, taking the equivalence class. And that gives me a sort of a finer set of initial data that again uniquely determines the metric up to gauge, but now the set of diffeomorphisms that are allowed are smaller because this parameter is now restricted. And this extends the corresponding symmetry groups by having this extra degree of freedom that goes beyond the diffeomorphisms of the surface itself. The third item, which I'll just mention very quickly, is I've assumed that the metric we're starting from is smooth and there are no singularities. But in many contexts, it's useful, this is something that Ben convinced me of, it's useful to consider a slightly larger class of metrics. So if I start with a configuration like this with my 2 surfaces, I can consider a boost, a normal boost, where I define the boost with respect to affine coordinates near the intersecting two surface. And that will map my initial data to some other initial data. But I can do this unusual thing where I let the boost act only, for example, in the right wedge and not in the left wedge. So so-called one-sided boost. And that acts on initial data by something called a kink transform. That was worked out in a paper by Venn and Raphael Busso. And it generates basically a gravitational shock wave. So if you act on your initial data with something like this, it generates a gravitational shock wave. And that's not included in our formulation because we're assuming everything is smooth, but it's possible to extend the formulation to sort of include this degree of freedom, basically by having the gravitational shock wave be just displaced slightly to the future of where we're setting our initial data. And essentially what it does is it takes our variable kappa plus, say, and it maps it onto something like this. Phi delta of, say, x plus minus epsilon. So it adds a delta function contribution to my kappa, and I can consistently define a larger phase space with one extra degree of freedom that will respond to this one-sided boost. Okay, so let me just say one last thing is with this extension of the coordinates in the phase space, I can then derive an expression for the symplectic form, and it has basically a contributions that look like integrals of the two null surfaces, if you like, bulk terms. It has a spin 0, spin 1, and spin 2 term, and then it has sort of a corner term, which is an integral over the intersection 2 surface, and that corner term has a coupling between the area element and another quantity that's acted on by this one-sided boost, which is something that's been seen before in specific models, but now we can see it completely generally here in a complete phase space. Okay, stop there. Thank you.
I'm wondering about this, these larger symmetry groups that you talked about out of the class 4, apart from the fourth one. So in these, you say that there are non-trivial diffeomorphisms on the boundary beyond just the diff S2 and the super translations, which are non-gauge. So this seems a little strange. You just took the Cauchy slice on the initial cut, the cut going from the bifurcation surface in that picture all the way to space like infinity. And you constructed the symplectic form on that as an integral of the symplectic current. It seems like a diffeomorphism supported somewhere in the future of that cut on the null horizon wouldn't do anything, wouldn't appear in the, it wouldn't affect any of the field variables on that Cauchy slice. So how is it possible that such a transformation is not gauge?
Yes.
So that's a very good question. So let me just try and rephrase the question and then. Okay, so so the question is, I'm going to take a Cauchy slice, and that contains data on that Cauchy slice should contain everything, and then I have some diffeomorphism that acts up here. So yeah, I didn't have time to go into this. So the charges that you get associated with these symmetries can be divided into two categories. Charges associated with the original global phase space, associated with data in this Cauchy slice. And for those charges, these would be gauge. But then people are interested in defining charges associated with cuts, like I mentioned. And that's a smaller phase space. And when you look at that, this sort of sub-phase space, then you're looking at, say, a data along here, then associated with those smaller phase spaces, it's not going to be gauge. Yes?
So you mentioned you used Ricciarduri and Demore to eliminate like theta and Hadricek on the horizon, right? Those are like the constraint equations. I was wondering, do you solve the final constraint equation that's like the surface deformation of the null surface? Those are like almost the diffeo. Those are 3 of the 4 constraints. I was wondering if this solves.
So when we actually explicitly parameterize the symplectic form, we make a number of approximations. So one of them is we assume we go to a smaller phase space where the up index normal, the perturbations, the perturbed optic normal is parallel to the up index normal. We also just worked a second order about stationary backgrounds. And because of that, we also just expand we worked second about a stationary background. So we just need to solve the Ray-Chowdhury equation to get an explicit symplectic form. But if we're going to do a more general calculation, then I think we would need to solve the other equations. Yeah, we haven't done that yet, that part, yeah.
So you mentioned the shocks case, but maybe a simpler scenario, or more generally a horizon will have these caustics or whatever. So does your formalism, can one deal with these caustics?
Oh, that's a very good question. And yeah, caustics do arise in real horizons. That is a limitation of what we're doing. Yeah, that's a good point.
Can I just ask, how do you, there's a question I always have about these things on the horizon. So the horizon is just a point in space-time, in the middle of space-time. So in the full phase space of the whole system, there's not going to be any special degrees of freedom there or symmetries. It's just part of the diffeomorphisms in the middle of the space, and it's all gauged. So if we were living in the space-time, we wouldn't necessarily measure these charges or anything. So what are the charges good for?
What are they good for?
The ones near the horizon, the one in infinity.
So I think if you're so there are different phase spaces, right? So one phase space is I'm just going to define a phase space considering of what's going on outside the horizons.
Yeah.
And so then the horizon is the boundary. And then there's a larger phase space like the maximum extended solution, in which case the horizon is down in the interior.
Yeah.
So I think what you say about it being pure gauge would be valid in that bigger phase space, but in the smaller phase space, it's not going to be true. And one of the things that's important about the boundaries I mentioned is that they, say for horizon, it's a unique function of the metric that you could compute at any point in your phase space, and then so it's not something that you pick arbitrarily, like you just pick up, a surface in millimeter space time, and it's sort of random.
But we think the interior is there, right? So if we have an astrophysical black hole, the phase space of the theory of that contains an astrophysical black hole, then it would be this one where there's nothing special happening at the horizon.
Sure, yeah, the local observer, but
just in the classical theory, if you can figure out all these charges, then you can start hoping to prove these global conservation laws for scattering outside the black hole, stuff like that.
Yeah.
I'm not sure I really.
There should be anything measurable. There should be a way of saying it in this phase space that doesn't have any of these charges. The interior is there, and we can still do whatever experiment.
Have a good answer on that.
Maybe just a comment about it, is that what Eanna is computing here are diffeomorphism charges, so they fall under another second theorem. So they actually are all shell of the constraints, are localized on corners, on codimensional two surfaces. And even if you are at the horizon, there is a physical one, which will be I plus.
You mean the one at infinity?
At infinity.
Oh yeah,
And that it will be localized there. So when you are off shell of the constraints, you can talk about the full horizon, but when you impose the Einstein constraint, you localize at corners. And that's where the
maybe that's what I'm saying, yeah, but then that kind of seems to me like it's also part of Scribe Plus, so it's a bit confusing.
Yeah, and the point is how you match, and that's exactly what Eanna was mentioning at the beginning, which is very hard.
You have one more follow-up?
I have a follow-up question, yes. In regards to the symplectic forms for the smaller cuts of the horizon, if you push along, I have a question about the consistency of these with the larger symplectic form. If you consider functions on phase space, which are observables under both symplectic forms, but they're observables on the larger phase space and the smaller phase space, do their Poisson brackets agree?
Do the Poisson brackets agree? I think they should, yes. Yeah, I believe so.
All right, let's thank Eanna